Okay, good morning, everyone, and thanks to the organizers for inviting me, and thanks to ICTS for having organized such a nice conference. I thought there was a really nice diversity of themes already, just in the first day yesterday, and I'm sure that is going to continue for the rest of the week. We're also treated, I think, remarkably well, looked after really nicely by ICTS, with nice accommodation, nice food, so that's an added bonus. Anyway, what I'm going to talk to you about this morning is something which might be in some sense a bit on the margins of the main themes of this workshop, but at the same time is in some way perhaps something that unifies quite a lot of the different ideas which people are going to be talking about and have talked about. I'm going to tell you a little bit about something called chemical reaction network theory, which is, I'll tell you what it is in a little bit, and I'll give you a little bit of its history and its background. And I'm a mathematician. My talk won't be massively technical. I've put in a few slides about the spirit of how some proofs work, but I probably won't have time to get to them, and that was my assumption when I was writing them anyway. But of course, I'll be happy to talk to you about. So I'll basically be presenting results, but I'll be happy to talk to you a little bit about proofs afterwards if anybody would like to hear about that. So if you have a system of interacting elements, and now really I mean pretty much anything, they could be chemical species, they could be elements of an ecosystem, they could be pathogen and immune response, they could be something, susceptibles and infecteds in an epidemiological model, for example. Well, naturally, you have this bipartite structure. And what this means is you have some kind of species and you have the interactions. And I find for a lot of purposes, it's helpful to separate those two things. So obviously, we always treat the species themselves as the objects of our model. But it's also useful to think of the interactions, in a sense, as objects as well. So the interactions would be that moment when the susceptible individual and the infected individual meet, and the susceptible individual becomes infected, for example. That would be an interaction. Or in the chemical reaction context, the moment when some particular chemical species meet, react together, and form a new chemical species, that would be the interaction. So you have this bipartite structure where species are involved in interactions, and the interactions affect the species. And this is reflected in the mathematics of the models that you get out of these so-called interaction networks. And obviously, you need to put a bit more flesh on it, a bit more mathematical detail in order to get some useful results. But that basic structure actually is responsible for quite a lot of useful mathematics, ultimately, and that's what I'm going to be telling you about. It's worth mentioning, given the context of this meeting, that a lot of things which don't appear obviously to be chemical reaction networks are chemical reaction networks in the broad and general sense of the term. So, for example, models in epidemiology, your standard SIS and SIRS models and so forth, are chemical reactions. It's just that the species that we're talking about here are, in this case, individuals, or in some cases, populations. So when you write down a system of reactions like this, like any of these reaction systems here, the arrow doesn't actually a priori tell you anything about the rate at which this interaction happens. Here we're free to superimpose that on top of this general structure at some later point. At the moment, this just tells us that, well, the following processes are occurring. Susceptibles are meeting infecteds and becoming infected. Infecteds can recover. Recovereds can become susceptible again. Infecteds can die. Susceptibles can be born and die. And recovereds can also die. Okay, so of course we could add more processes into this model, but that's what that's saying to us. It's just telling us the very broad structure of what's happening, and it is a chemical reaction network in its structure. So I like to point this out because I think people outside the field who are not particularly interested in chemistry per se don't realize that the formalism, and many of the results as well, apply well beyond chemistry itself. I'll come back to that perhaps at a later point. Now, Personally, I'm interested in ODE models of chemical reaction networks. So chemical reaction network theory includes people who do deterministic stuff and stochastic stuff. And within the deterministic people, it includes people who do things in continuous time, continuous space like myself, or people who do things in discrete time. Perhaps the biggest strand of work is the ODE modeling community, so the people who make the assumptions which give rise to ODEs. I'll talk about that in a second. And within this, what makes something chemical reaction network theory, as opposed to more general just modeling of chemical reaction networks, is you try to make claims which are parameter-free. So you try to make claims which are based on the structure of the network as far as possible. Now, to some extent, you have to bring in some physical assumptions to get something interesting out of it, but those may be quite broad and general physical assumptions that you bring in. And this parameter-free theory is what is usually referred to as chemical reaction network theory. Historically, that's what it's meant. So what are the kind of things people have asked about? So first of all, just as a kind of matter of history, I mean, this field has been around. Different people will differ on how long chemical reaction network theory has been around, but it was certainly around in the 70s. That's something that people can agree on. And there were these seminal papers of Martin Feinberg in the US and Horn and Jackson in the UK, which proved a kind of suite of theorems, a suite of results, which are kind of really elegant, really mathematically beautiful and general results about the behavior of chemical reaction networks. And some of these are called the deficiency 0 and the deficiency 1 theorems, in case you happen to have heard of them. So that was really the beginning of, let's say, modern chemical reaction network theory. But there's been a lot of development in the last 15 years as well. So since about the early 2000s, the early to mid 2000s, there's been quite a lot of work. And this work has been around what you can say. I've just put a few themes here. There are a lot more. But what you can say about equilibria of these systems. Do they have to be unique? Do they have to be stable? Can you have different kinds of bifurcations? What you can say about other interesting behaviors. Can you have oscillation in chemical reaction networks? Could you have chaos? There's a big and interesting strand of work around the question of persistence. And in fact, one of the big open questions or semi-open questions in chemical reaction network theory is around persistence, where persistence means, I'll tell you a bit more, I'll give you an example of a persistence result. Persistence means, can trajectories of the system go to the boundary, roughly speaking? So if you're an epidemiologist, you're interested in persistence because you want to know whether you can eradicate a disease. And there we take eradication to mean that the number of infecteds goes to 0. So in terms of your state space, one of the variables is going to 0, and we're eradicating that. That system is not persistent. Right, that would be an example of a non. So I think the term actually probably comes originally from epidemiology, this notion of persistence. But it's an important question in chemical reaction network theory. Which chemical reaction networks are persistent? And there's a big open question connected with that. There's also been a lot of work on trying to play with different kinds of kinetic assumptions to make chemical reaction network theory more widely applicable. So for example, to models in biology, where you can't always assume mass action kinetics. So that's, in fact, really how I started working in the field, is I was trying to generalize some results with mass action kinetics to non-mass action kinetics. So it turns out that that can quite often be done to bigger classes of kinetics than mass action. And there's a lot of kind of work which is classical dynamical systems work, where you're trying to find things like Lyapunov functions, you're trying to make claims about global stability of objects, and so forth. I'll give you examples of some of these results. So these ODE models, what's the kind of physical setup that you have in mind when you construct these ODE models, at least in the purely chemical context? Well, the setup is you've got some kind of a container, and within this container, you've got some chemical reactions going on. The container may be closed or open or semi-open. Semi-open meaning some things can flow in or out, but not necessarily everything. Or you can have kind of active transport across the walls of this container. Imagine it's a cell, so some things might be able to disappear, flow out, but through some kind of process where they react with something else and together they disappear, and so forth. And I'll call a network fully open if it includes all of the reactions. So all of the inflows and outflows of every possible species, and we'll call it fully open. Everything can go in and out of that. Fully open networks are in some sense a bit easier than other kinds of networks. They allow more stronger results. I'll give you examples of that. So I said that I'm interested in parameter-free theory. I'm interested in structure-based claims. So the first thing we have to clarify is what do we mean by structure of a chemical reaction network? And what we mean by structure is literally what is written down when you write down a chemical reaction network in some form like this. So when you write down something like this, if that's all the information you have, then we'll say all you know about the reaction network is the structure of the network. And in particular, what you don't know is what exact speed each of these processes occurs at. So how fast each of these processes is occurring. What does that arrow actually represent? Now, there are different ways of drawing a reaction network, if you like. There are different graphs which are associated with it. This one here, for example, is called the complex graph. It's a classical representation which occurs in many of the early results on chemical reaction network theory, like the deficiency theorems I mentioned earlier. Here's another one. This is called the Petri net graph of a chemical reaction network. So for example, this little dot here represents a reaction, and this particular reaction is the reaction where species X gets converted into one lot of W and one lot of Z. So that's X goes to W plus Z, and that occurs there in the reaction network, and then this dot represents another, this vertex represents another reaction. This is X plus Y goes to 2Y, which occurs in the network. So each of the filled in dots is just one of the reactions, and each of the other vertices is the species, and that network obviously is just another representation. It's just another way of drawing the reaction network. But the reason I'm showing you these is because there are a lot of results which are about doing computations literally just on these graphs and then making claims based on those computations. Okay? Sometimes computations on those graphs combined with some other kind of computations as well. So the bit that's missing when you're just looking at the combinatorial structure is the so-called kinetics. So how fast do these processes proceed? We've already heard mass action kinetics mentioned a few times in talks yesterday. So mass action kinetics is the most commonly used kinetics amongst chemical modelers, but that's less true once you move into biology. So once you move further away from a kind of idealized engineering context, it becomes less true. You've got complicated geometries, you've got reactions taking place on membranes, you can't assume that things are very dilute in some situations. In some situations, of course, things are so dilute that you've really got a stochastic process and you can't use ODEs at all, but we won't go all that way. But anyway, mass action kinetics is historically the most often used kinetics in chemical reaction networks, but you might want to use something weaker. So for an example of something weaker, something which makes less strong assumptions would be something like weakly monotone kinetics, which says, roughly speaking, that reactions can proceed if and only if all the reactants are present, and the rates of a reaction depend only on the reactants. So if something doesn't appear as a reactant, then it can't affect the rate of a reaction. You might argue with that assumption. And another one is that reaction rates increase strictly if you increase the reactant concentration. So any particular reactant, you increase its concentration, the reaction speeds up, provided you hold everything else constant. Again, mass action, of course, falls into this. It's a special case of weakly monotone kinetics, but this is a much, much larger class of functions than mass action. Okay, so it's a much weaker assumption on the kinetics. Now, supposing you're trying to prove that a chemical reaction network can't do something, so you want a negative result. This is impossible. Obviously, you've got your best possible result if you prove that using some very large class of kinetics. You're saying that for all of the kinetics in this very large class, this is impossible, so you've got a better result. So in general, we try to prove those kind of results under the assumption of, say, weakly monotone kinetics or some other weak assumption. On the other hand, if you want to prove that a reaction network must do something, say it must oscillate, you would like to say something more specific, like it must oscillate with mass action kinetics for some choice of the mass action rate constants. That's a better result then saying it must oscillate for some choice of weakly monotone kinetics, which is a very large choice of functions, class of functions after all. So when you're proving existence results, you'll mostly work with narrower classes of functions. And I'm just mentioning that because when I show you results, that'll be the template that I follow, and I'll just mention briefly, yeah, this is true for mass action, or this is true for weakly monotone kinetics. So in general, the results are in the direction of the best possible result that we can get as far as possible. So let me pause there with the kind of generalities and give you an example of a specific result. And I really like this result. It's one of my favorite results, and it's an example of something which is pretty much entirely a structural result about chemical reaction networks. Now, it's got a bit of jargon in there, which I'll unpack a little bit for you. It's a result of Schinner and Feinberg from a few years ago. No, so it's a recent result. And it says that a weakly reversible concordant chemical reaction network is persistent. So I've mentioned at least a couple of those words before, but some of them might be new. So let me just kind of go through them quickly. So the first term there, weakly reversible. Weakly reversible is a property of one of those graphs that I showed you. In fact, of the first one, the so-called complex graph. And it just says that every connected component of that graph is strongly connected. Another way, let me kind of skip back a little bit to this graph here. So this graph, this reaction network is not weakly reversible because I can get from one of these combinations of species, these combinations are called complexes, so I can get from this complex, say, to this complex, but there's no way of getting back again. So a chemical reaction network is weakly reversible if whenever you can get from one complex to another, there is some path, not necessarily the most direct path, but some path which will take you back again to the first complex that you came from. Okay, so that's the meaning of weak reversibility, and it's a very easy to check, computationally kind of easy thing to do. It's just Dijkstra's algorithm applied to this, if you're familiar with that. So our first hypothesis in that theorem is that the chemical reaction network that we're interested in is weakly reversible. And weakly reversible networks are of particular interest for a variety of reasons, which I won't go into, but there's a lot of results which are specifically about weakly reversible networks in chemical reaction network theory. The second assumption there is that the chemical reaction network is something called concordant. That's a little bit more complicated to unpack, but the spirit of it, or one way of considering concordance, is you can associate with the chemical reaction network a polynomial. And by the way, when you associate this polynomial, you're not assuming some kinetics. It's associated in a completely general way, just based on the structure of the network. So you can just look at that picture and associate with it a polynomial. And you can ask really a question about whether certain minors of this polynomial, I'm saying minors of a polynomial, which doesn't make sense. It's actually that you're associating with it a matrix, and you're asking a question about the matrix, but this can be recast as asking a question about polynomials and whether certain polynomials are positive or not that you associate with the network. Again, it's a computable condition. Okay? I'm a bit uncertain about its complexity, so as a network grows in size, how hard is it to actually make the claim that a chemical reaction network is concordant? But certainly for medium-sized networks up to pretty large networks, it's quite easy to compute whether a chemical reaction network is concordant or not. Okay, so it's a structure-based computation that you can do in a network. And if a chemical reaction network satisfies those two hypotheses, then it is persistent. And this means that if you take an initial concentration of chemicals where every component is positive, so every chemical has positive concentration initially, roughly speaking, concentrations can't go to zero. Okay, you can't have limit sets which intersect the boundary of the state space, more precisely speaking. And the assumptions on the kinetics are basically absent, as not even weakly monotone kinetics. You really have to assume, there are some very, very weak assumptions on the kinetics underlying that result, but they're so weak as to be essentially absent from my point of view. So it's a completely structural result, and it's not completely easy. The original proof is really quite complicated. There's a somewhat simpler proof in a paper, in the appendix of a paper, which is not really about this, but where we dealt with this result as one of the results we were considering, which is more elementary, which just kind of focuses on trying to prove this from first principles and without going into different areas of chemical reaction network theory and bigger results. But anyway, that's an example of a combinatorial chemical reaction network theory result, and one of my favorites as it happens. Okay, just a brief digression, a little kind of technical slide. So I said, okay, we're interested in ODE models. So how do you get an ODE model from a chemical reaction network? How do you write down an ODE model if you're just given one of those structural diagrams? Well, there's kind of standard and I think familiar probably to a lot of people who do modeling, so a lot of people in the audience. You have to write down some functions for the rates of each reaction. You have to write down a matrix called the stoichiometric matrix, whose entries tell you about the net production or consumption of each species within each reaction. So the ijth entry tells you about the net production of species I in reaction J. And you put that matrix and this vector of rate functions together, and you get a set of ODEs, which tells you about the evolution of the species. The thing to note about this system of ODEs is that it's got this natural structure where the stoichiometric matrix comes in first as a first factor, and then this vector of rates comes in as a second factor. And this throws in various kind of mathematical complications, let's say. The fact that you've got this matrix coming in at the start. One of the things that it results in is that clearly the right-hand side of this differential equation system belongs to the image of gamma, where gamma is this matrix, the stoichiometric matrix. Now the image of gamma may be of lower dimension than the state space. Right? The image of gamma lives in the state space, the space of concentrations of your chemical species, but it might be of lower dimension, so it might be a subspace. So in the picture that I've drawn here, the image of gamma is two-dimensional and the state space is three-dimensional, so you've got three chemical species. But if you like, you've only got two linearly independent reactions. You might have 10 reactions in there, but all of them, if you like, all of their reaction vectors are combinations of just two linearly independent vectors, let's say. In that situation, you have all of your dynamics going on these two-dimensional subspaces of your state space. Okay, so everything is restricted to these lower dimensional subspaces. So if you make a claim about something can oscillate and this periodic orbit is unique or something like that, what you mean is unique relative to the subspace on which it lives. It's a kind of slight technical point, but it's worth bearing in mind. And actually this is a complicating factor in several arguments, I should say. What are the behaviors that you might ask about when you're asking about a chemical reaction network? There are a lot of standard things. I haven't put everything that you might ask about by any means here. You might ask about, I've highlighted two because I'll talk more about these two, oscillation and multistationarity. Multistationarity means the possibility of more than one equilibrium on each one of those level sets. You might talk about the stability of objects, global stability or local stability of objects like equilibria or periodic orbits. You might ask about persistence, which I've mentioned. You might ask about something more exotic, like chaos. Is that possible in this reaction network? And there are a number of other things which I haven't mentioned. You might ask about identifiability. So for example, identifiability can also be a structural property of a chemical reaction network, or the lack of identifiability can be a property of a reaction network as well. So let me just give you a few examples. I'll give you examples of applications of results where something is forbidden, so where something can't occur. And all of these are under the assumption of weakly monotone kinetics. So here's an example of a medium-sized chemical reaction network. It actually, I forget its biological origins, but it is a network of the kind, it's a kind of generalization. It's one member of a family of networks of a kind which arises through various enzymatic mechanisms in biology. And I can claim that this network doesn't allow multiple equilibria. Okay, I mean, I would have to unpack that to make it precise. More precisely, it doesn't allow multiple positive non-degenerate equilibria on any given invariant set. Those invariant sets, incidentally, are called stoichiometry classes. And how can I make this claim? Well, I can make this claim just based on computing something about each of the cycles in this diagram that I've drawn. Incidentally, this diagram is neither of the two graphs that I showed you earlier. It's kind of similar to a Petri net graph, the second one of those graphs, but it's actually a slight modification of that. But it also can be derived from the network structure alone. Okay, it's something called a DSR graph. And I can compute something about its cycles and about how they intersect. And this computation is obviously implemented algorithmically, and it's fairly easy to do. In fact, this one is so small and easy that it can be done by eye. You can just look at the cycles, check how they intersect, and say, right, it satisfies this condition, which we call condition star, and hence this chemical reaction network forbids multistationarity. Can't have multiple equilibria. Okay. Here's another example. This one, again, is structure-based. It's a very artificial little network, but again, it's just one member of a family. This family is quite interesting for a variety of reasons, because odd members have one kind of behavior and even members have another kind of behavior in this family. But for example, this member of the family can't have a non-trivial attracting periodic orbit, or pictorially, this situation is ruled out. So if you look at one of the stoichiometry classes, one of these invariant sets, that you won't find a periodic orbit, at least you won't find an attracting one on it. And I'll tell you a tiny bit about where these results come from later, but for the moment I'm just giving you examples. Here's another example. Here's a little chemical reaction network. Here you can make a very strong claim with weakly monotone kinetics about this network, and the claim is that all orbits on each of these stoichiometry classes, in fact, converge to a unique fixed point. So there's a unique fixed point on each stoichiometry class, and all orbits on that stoichiometry class converge to that fixed point. So it's a very strong global stability result. It's about as simple behavior as you could hope for, and you can make a claim about this. Again, obviously, it's not about this particular network. It's just that this particular network satisfies the hypotheses of one particular theorem, and those hypotheses are easily computed just by looking at this reaction structure. Easily confirmed by looking at the reaction structure. There's quite a lot of different areas of maths which underlie these results. There's theory about the injectivity of functions. There's some kind of basic theory, like the fundamental theorem of calculus, for example, but applied cleverly, applied non-trivially. There's quite a lot of construction of Lyapunov functions, but again, sometimes constructing Lyapunov functions can be quite non-trivial when you're trying to do it with limited knowledge. You don't know the values of parameters in a system, so you have to do it either simultaneously for all elements of this, for all different reaction networks, or either you find one Lyapunov function which works for everything, or you have a family of Lyapunov functions, each of which works for each of the different networks, and in either case, it can become rather complicated. A lot of the results, particularly mine, apply something called the theory of monotone dynamical systems, which I won't go into, but it's a kind of elegant and big theory within dynamical systems about dynamical systems which preserve a partial order, and so forth. So a lot of theory from algebra comes into it as well, from linear algebra, from abstract algebra, from exterior algebra, and so forth. So those were results where you rule out some behavior in a sense. I mean, even the one where I said everything converges to a unique equilibrium, that's actually ruling out a lot of possibilities. There's certainly no chaos, there's no oscillation. So you're ruling out complicated behaviors. A different kind of result is where you say that some complicated behavior must occur. You must have multistationarity, or you must have oscillation, for example. So I'll give you some examples of results which look like that, but I'm going to focus in particular on a class of results which I find philosophically appealing and which I started to work on for that reason, which is results where you look at a network and you find an interesting subnetwork in some sense, and you know something about this subnetwork, and then you want to say, because I know something about this subnetwork, consequently this whole network must have some behavior, must have this behavior. So supposing I know that the subnetwork allows oscillation, I would then like to be able to claim that the whole network consequently allows oscillation. Those results I call inheritance results, because the whole network is inheriting some behavior from the subnetwork. Okay, so I'm interested in particular in inheritance results. So let me give you an example of an inheritance result. This was the chemical reaction network I put up earlier just as an example to show you the different graphs. Within this chemical reaction network, if I take away the grayed out portion, I'm left with just this part, and if I just ignore the identities of the particular chemical species, the letters I've given them, I'm left with this little subnetwork, which I'll call a motif. okay, because that's a kind of popular term in biology. It's a motif. It's a little piece of something in a larger network. Now, this motif I can show in various ways admits stable oscillation with mass action kinetics. So if you have a chemical reaction network, it actually has to satisfy an additional condition, which is it must be fully open. If you have a fully open chemical reaction network, which includes this motif in it, then it admits oscillation. That's what I'm going to claim as a result, and that's an example of an inheritance result. Okay? Obviously, the result is not about this particular motif. It's about how, if you find a motif in a fully open network, and then you look at the full network, whatever behaviors, certain behaviors of that motif will also transfer into behaviors of the full network, will translate into behaviors of the full network. I'll show you where that kind of result comes from. Now, when we talk about subnetworks and modifying networks and doing things to chemical reaction networks, there are certain obvious things that you can do. You can delete reactions, so just get rid of a reaction from the network altogether. That means getting rid of one of these vertices and all of its incident arcs. You can get rid of a species. That's a bit more strange. You get rid of, say, this species and both of its incident arcs, which doesn't mean that you get rid of this reaction, but you've changed it from being x goes to w plus z into being x goes to z. So it's changed its identity. And this reaction has changed from w goes to x into x is born from nothing. 0 goes to x, if you like. So x has flowed into the system somehow. So when you modify a network by taking away species, that's a valid modification at a theoretical level, but it's a bit harder to interpret at a practical level. Another kind of modification that you might do to a network is you might, say, remove some intermediate process. So y plus z goes to x, goes to w plus z. I'm going to get rid of the goes to x part and just have y plus z goes to w plus z. That would be an example of removing an intermediate, or conversely, of course, you can add in intermediates in a reaction. So that would be a consequence of maybe you caricatured your process first time round and you said A goes to B. And then you looked a bit more closely at the biology and you realized actually A doesn't go directly to B, A goes to C, which C then goes to B. Right? There was something happening in between, and I'm going to add that in. So inserting or deleting intermediates is an example of a process that you might do to a network. And I'm just interested in exploring quite systematically how these different modifications that you might do to a network, in particular modifications which build a network, how they affect the behaviors, the possible behaviors of the network. Now, it would be very surprising if making a network more complicated didn't allow you to introduce more interesting behaviors. We expect that to happen. But we kind of don't expect that when you make a network more complicated, you're going to lose interesting stuff. Right? So if I've got an oscillatory subnetwork, and I make it a component of a larger, more complicated network, I kind of expect the larger network to be oscillatory. That's not always true, as it turns out. There are some counterintuitive examples that I'll show you. So embedding a smaller network in a larger network can destroy complicated behaviors. But the inheritance theorems tell us when that doesn't happen, if you like. It tells us when you can assume that because you see a small network with some property, the bigger network also has this property. So here's an example of a result. It's actually an amalgamation of several results in 2 different papers. So I've used this less than or equal to symbol deliberately because this is a partial order on the set of all chemical reaction networks. So I'll say that R is an induced subnetwork of R prime and write it in this way. If R can be obtained from R prime by deleting species and deleting reactions. Okay, so that's these, in this previous slide, just these top 2 operations where you delete some reactions, you delete some species, and if you can obtain a network by deleting species and deleting reactions, then we'll say that the smaller network is an induced subnetwork of the larger one. This is just following graph theoretic terminology. It would be an induced subgraph. The smaller graph is an induced subgraph of the larger graph. And here's a result. If you've got 2 networks, R and R prime, and R is an induced subnetwork of R prime, and additionally, they're both fully open. So that means that all species can flow in and out, and this is important for this result. Then if the smaller network admits non-degenerate multistationarity or non-degenerate oscillation, and I can replace some of these words with other things. Incidentally, I could make it quite a general result, and I could say, if you have some non-trivial hyperbolic behavior in the dynamical system sense on one of these stoichiometry classes, then this will be preserved in the larger network R prime for some choice of parameters. So this is a mass action result, some choice of rate constants in the larger network. Another way of phrasing it is that non-degenerate multistationarity or oscillation is inherited amongst fully open chemical reaction networks with this partial ordering, the induced subnetwork partial ordering. So for a mathematician, that's the way I like to phrase it, but maybe that kind of reduces the intuition. It's easiest just to think about removing species and removing networks to get the smaller network, removing species and removing reactions to get the smaller network from the larger one. So here's our earlier example, the one I gave you a few slides back. So here we had the full network, and I kept only this part of it, so I removed two reactions. As it happens, actually, I also ended up removing the species W, which had now become redundant because it didn't figure in any reactions after I removed those two reactions. I was left with a smaller system. This smaller system I know oscillates. Its fully open extension oscillates, so that's if we also allow inflow and outflow of all species, and consequently, the fully open extension of this larger system oscillates. Now, interestingly, this claim fails if we get rid of the assumption that the networks are fully open. And here's a little example of how making a network more complicated can actually destroy interesting behaviors. So the first of these three chemical reaction systems here, what I've called R here, admits oscillation. You can find it in numerical simulations quite easily. You'll see the variables oscillating for certain choices of rate constants. In the second one, I added in some species into some of the reactions. So I said instead of Y just degrading and being created, actually to degrade or to be created, so its birth and death process I'm going to make a bit more complicated, it needs to meet a molecule of V in order to die. And when it's produced, a molecule of V is also produced. Okay, so it's a kind of small change to the network. I'm just adding in this redundant additional species which gets created whenever Y is created. And this species doesn't take part in any of these other reactions. I do the same with Z. Another species is created whenever you create Z and degrades whenever Z degrades. This network doesn't oscillate. It can be proved that this network, in fact, belongs to a particular class. I use one of the classical theorems of chemical reaction network theory, the deficiency zero theorem. It's an example of a weakly reversible deficiency zero network, and it certainly doesn't admit stable oscillation. In fact, it doesn't admit oscillation. I make it a bit more complicated still. How do I do this? I just take this network R prime, and I now say, well, V and W can themselves independently flow in and out of your container, right? So I add birth-death processes for them, if you like, inflow-outflow processes. And now again, we get oscillation here in R double prime. So I'm just putting that example in to illustrate that it's a bit subtle. So making quite small changes to a network, which are quite natural, can destroy the possibility of some interesting behavior, and then making other small changes can introduce it again. And the previous result only tells us about fully open networks. So it doesn't tell us that, we can't predict that R prime oscillates because R oscillates. In fact, it doesn't. Okay, we can prove that it doesn't. I'm going to probably be quite brief with the remainder of my material because, it's not the detail is not too interesting, perhaps. It's the spirit of it. So how do you prove a lot of these things? Well, you prove a lot of these things by putting together a set of basic modifications that you can do to a reaction network and then somehow combining these together to get more interesting results. So I've put some examples of basic modifications here. So one basic modification is introducing a so-called dependent reaction. And the simplest example of that is if you have, say, Y goes to X, and you now introduce X goes to Y, whose reaction vector is just minus the reaction vector of your first reaction. That's an example of introducing a dependent reaction. So that's an allowed modification, which preserves a lot of behaviors, preserves, in fact, arbitrary hyperbolic behaviors. Another modification is taking the fully open extension of a reaction network. That means you have a reaction network, and now you introduce inflows and outflows of all species. Right? You take a closed container, and now you make it porous, if you like. Everything can flow in and out. That's an example of a modification. Here's a modification where you introduce a trivial species into reactions, which means that it figures, whenever it figures on the left-hand side of a reaction, it also figures on the right-hand side with the same stoichiometry in the same quantities. So there's no net production or degradation of this species in the network. So that would be introducing trivial species. That's an allowed modification. Here's a slightly more complicated one. You can introduce a species into any reaction however you like, or any set of reactions however you like, provided you also introduce its inflows and outflows. And that's another example of an allowed modification on chemical reaction networks. So the theorem is that, the theorem again stated in a simpler form than perhaps it can be stated in a less complete form than it could be stated, is if you create a network from a smaller network through these allowed modifications, through a sequence of allowed modifications, then the larger network inherits all the hyperbolic behaviors of the smaller networks. So for example, non-degenerate multistationarity, non-degenerate oscillation, and perhaps anything else. And actually the previous result I showed you about fully open networks is just a corollary of this, because if you have two fully open networks and one is an induced subnetwork of the other, then in fact, the larger one can be made by a sequence of these basic modifications applied to the smaller network. So it just follows immediately. The result that I said about fully open networks follows immediately from this. Okay, there are other modifications. So the one that I'm perhaps most interested in, the remaining one that I'm perhaps most interested in, is splitting reactions. So here's an example. So there's another one here which I've put in A, which I won't go into. But here, supposing you have a reaction network which was originally x plus 2y goes to 3y and y goes to x. And now suppose instead of x plus 2y goes to 3y, I insert something in the middle there. X plus 2y goes to something else, some other combination of species involving some new species, in this case z, and now that goes to 3y. That's another example of a modification which preserves interesting behaviors in chemical reaction networks. It preserves multistationarity, it preserves oscillation. Let me show you that in practice. Here's a little network, and you can do some numerical simulations choose these rate constants appropriately, and you'll find it starts to oscillate. And now I'm going to take that, and this is the original network again, just so that it's on both of these slides. I'm going to take that network, and I'm going to split some of the reactions. I've split this one, and I've inserted a new complex here. I've split the x goes to 0 part here, and I've inserted a new complex there. I don't even have to do my simulations. I have, of course, done them to check, but this new reaction network admits oscillation as well. Moreover, I actually know how to choose the rate constants in this new one so as to get oscillation, roughly. These are perturbation theory. In fact, this is a singular perturbation theory argument. So I know the regions of parameter space where I get oscillation. And okay, so how does the whole thing fit together? The whole thing fits together once you know this full set of modifications. It's not a full set, but every time you prove one of these results, you get another modification that you're allowed to do to a reaction network, which preserves interesting behavior. And we're obviously trying to build up the zoo of such modifications. And together, these give us a partial order on the set of chemical reaction networks. And whenever we find some interesting behavior in a lower member of this partial order, it is automatic in all higher members of this partial order, everything above this lower reaction network. Okay, so that's the kind of goal of this theory, of this inheritance theory for chemical reaction networks. And you often get other things as byproducts. So for example, if you take a reaction network, say x goes to y, and you introduce an enzymatic mechanism, so now it's x plus enzyme goes to complex, which goes to y plus enzyme, that's an allowed modification as well. Why? Because it can be built up through a sequence of allowed modifications. Okay, so in fact, in this partial order, this one is greater than this one, and so this was something we were allowed to do to the network. I'm obviously caricaturing and simplifying. There's a lot more to it than I'm saying, but that's the spirit of it. So you can build up other mechanisms which are allowed modifications. I'm going to skip the bit talking about proofs because I'm mindful that I have exactly 21 seconds left. And I'm also going to skip the bit about some of the difficulties. Okay, I'm just going to come to, what are the conclusions of this work. So the conclusions of this work are, one, that chemical reaction network theory provides some interesting, non-trivial claims, and that these claims extend beyond chemical reaction networks. They extend to other things which are formally chemical reaction networks, including epidemiological models, immunological models, and so forth, in some situations. I presented a lot of those results more narrowly than I could have done, just to make them more presentable. So quite a lot of them are proved under a variety of different kinetic assumptions, but I just said, okay, mass action or weakly monotone kinetics, because that was the simplest catch-all, which was included in all of the assumptions of the different theorems. So there's kind of more to be said. Another thing that's worth mentioning is that there's a lot of open questions still to be resolved. And I'll be happy to chat to you about what are some of those open questions. There are some unsolved conjectures in this area, which I think makes it a more exciting area. After all, if it was all done, then it wouldn't be so interesting. And I've put a list of a few publications from which these results are drawn, which also includes a list of some of my collaborators with whom I've worked on these results. So the names that you see in those publications are the collaborators who've contributed to the results. I want to finish by thanking you again, and thanking you for your attention.
Thank you very much.